Muy buenas tardes a todas y todos honorables miembros del Presidio, invitados e invitadas especiales que nos distinguen el día de hoy con su presencia. Querida comunidad universitaria, en nombre de la Dirección de Educación Continua, les damos la más cordial bienvenida a la Universidad Iberoamericana, Ciudad de México, a este magno evento, la NASA en la Ibero, un fascinante viaje al mundo de la inteligencia artificial, de la mano de Graham Mackintosh, especialista de la NASA, donde descubriremos cómo la IA está revolucionando nuestra forma de conquistar el cosmos, generando un sinfín de posibilidades para las próximas generaciones de la humanidad. Le damos la bienvenida a Graham Mackintosh.
Thank you so much, first of all, for allowing me to speak in English as I give this presentation instead of your beautiful language here in Mexico. Also, of course, I want to thank the Mexican Space Agency, Guillermo at AEM, for helping to coordinate this, Erica, her colleagues, and IBERO's leadership for arranging for me to come here. Now, you think you've come to see me, it's the other way around. I've come to see you. I'll explain why in a moment. If we could switch the display to my laptop. Very good. We've been hearing introductions. It makes it sound like I'm the star of the show, and I'm not. I'm here to tell you that the star of the show is you. I'm old. I have gray hair. You don't. Do you know what we call you at NASA? You young faces with all the energy. You're the Mars generation. You're the ones that are going to take us there. So I may tell you some ideas that I have about artificial intelligence, and I hope you find it interesting. But my job is to encourage you to think beyond those ideas and to do them. Now, I know this will happen. And the reason is because we are all explorers. NASA is in the business of exploring, to going places we've never been before, but we explore intellectually, scientifically, socially. All of these different ways of expanding our horizons come together. That's how it works. So you are all part of this. And I believe artificial intelligence is a big part of how we will be explorers together and be successful. Here's how I'd like to discuss it with you. First, I want to talk about why I think AI is important, the imperative of AI. That's new. I didn't know I had to connect to the box, whatever that is. Yes, exit. Okay, and then I want to talk in general about AI and space exploration, and then I'll talk to you about some of the projects that I am particularly involved in or leading. And then we, of course, have some discussion. So to get into why AI is imperative, why it's important, it almost implies, well, because it's all going to be amazing, right? It's going to be wonderful. It's all good. In English, we have an expression when something important is being ignored and it makes it very difficult to engage. It's called having an elephant in the room. The elephant in the room is the thing that everyone knows is there. It's a problem, and no one wants to talk about it, so it makes it hard to embrace some of the opportunities. And those problems are very real. I want to talk to you just for a moment about something that I'm sure you think about, you read about it. AI is scary. It's scary. It's making changes in society that are difficult. So the elephant in the room is not just about AI, to be fair. AI is a technology. So technologies amplify who we are and what we do, good and bad. Let's take the incredible improvements in aircraft. I mean, aircraft can be used to drop food for people who are starving. It can be used to drop fire retardant, to put out fires that are destroying homes. But they can also drop things that destroy homes. They are technology amplifies who we are. Rockets are technologies. And I love to hear about what the AEM is doing with Meridia. They're going to develop a brand new space center in Mexico. Think of it like your innovation hub, but for space. And rockets like these take satellites, which allow research like this that happens right here, just a few years ago. I've read these papers. They're fantastic. Fantastic innovation on image processing. This particular group of individuals used a technology we'll talk about later called support vector machines, but that's not the point. The point is that was enabled by the rockets. But rockets can do evil as well. So that's, in a nutshell, the elephant in the room. Now, technologies fail us when they stop working. They do their job, but in ways that we didn't expect. They have unintended consequences. They also cause pain if they accelerate and improve faster than we as a society can adapt. And, of course, they don't help the human condition if they're used intentionally for evil. And AI can be used that way, right? I mean, this is an individual, a mother, testifying to Congress how a deep fake voice of her daughter tricked her into believing that her daughter had been kidnapped. Even here in Mexico recently, right? You have Ms. Shobam having a video put out declaring everyone should invest in a financial fraud scheme. Of course, she didn't do that. It was all deep fake. So misinformation is just one example of AI being used in a way that is intentionally harmful. Now, I said this is true of any technology, but I will admit that AI is complex. Part of the elephant in the room with AI is because it's hard to constrain what it does without limiting the creativity that can come from AI. And we need that to solve difficult problems. It changes. You know, when you build a plane, it stays a plane. It doesn't change. But when you build an AI model, it learns and self-adapts and becomes something different than what we made. That's exciting, but it's difficult. Its capabilities are incredibly improving fast, and what happens to jobs? How do we retrain? How do we become partners with AI instead of under it? And so on. Very difficult to regulate. It's easy to get at this technology. It's very generalizable. And in a way that is difficult to put our heads around, here we are trying to make something that it will become better at us at the very thing that makes us the dominant species on this planet. That's unusual. So, interesting to think about. My approach to the elephant in the room is to say, let's just focus on the good things and have that just outweigh the other things. And space exploration is a unifying, uplifting thing for humanity. It always has been. So I feel good about using AI to drive innovations that will help us solve some of the important problems for humanity: healthcare, education, applying AI to making you better educated than ever. applying it to existential threats, climate change, and so on. But I like to apply it to our quest to understand the universe around us. So with that, let's take an example and understand what's AI. What is AI? Just for some of you may know it well, some may not. So AI is a very broad definition. It covers all kinds of things. In general, it aims to show, to mimic, and emulate biological intelligence. And often, once we see a computer do it, we go, oh, that's not intelligence. And we move the goalpost. But that's okay. It covers any technique that lets it mimic human intelligence. Machine learning is statistically driven typically. I happen to be most involved in deep learning, where you have a mathematical representation of neural connectivity. And it aims to use artificial neurons that are connected in a way that can take an input and produce an output that is valuable in some way. In this case, just recognize a written number. So literally the little bits and pixels that make up the number 2, they go in. Each neuron is connected to another layer with different weights. And eventually, the neuron that gets the most energy out of the network is the answer, 2. The way it's trained is to show it lots and lots of examples and do something called backpropagation. So when it gets it wrong, you find the neuron that was most responsible for the wrong answer and you punish it by changing the biases and the weights. And you do this over and over, because when you change something to make it work better for the number 4, that might make it worse for the number 9. And you have to tweak it and change it. You have to do this millions of times. And the mathematics for this are very hard. That's why the computers doing this are so big. So think of it this way. This is a representation of a very simple perceptron neural net. To give you a sense of scale, this is basic neural net architecture. To make it understandable to our eyes, 2% of the connections, those lines, are actually shown. Otherwise, it would just be a big white box. It's huge. And this is simple. This is just to do number recognition. So it's an interesting field. And let's go through an example. And I'll show how it applies to everyday life, but also space exploration. So this is called an autocorrelator. What it does is take lots of neurons, crunch it down into just a few, and then go back out again. It has one job: to try and produce at the end what went in. So it wants to decode and create that exact same image. And to begin with, it does a terrible job. It doesn't know anything. But each time you say, no, 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 you're trying to make that, it gets a little better, and gradually it does a pretty good job. Now, for the mathematicians in the room, we train that with something called a loss function. That's just the expression there is just a fancy way of saying the difference between what went in and what came out. That's how we train the neural net. So imagine how useful this is, because once it's trained, the difference between those two becomes also a useful score. It says, this is different than what I've seen. This is an anomaly. If you train it over and over to do a good job with the number 6, and then you show it something completely different, it's going to do a terrible job of that. It hasn't seen that before, so the whole neural network is not set up to do it. So the anomaly score, that's a terrible 6. It's not a 6. That's an anomaly. So that's the beauty of autocorrelators. It's unsupervised learning. And you do this all the time. When you buy a new car, at first you're like, oh, does that sound normal? I'm not used to this car. And gradually you get used to what your car sounds like. And you're happy. The car's working perfectly. And you become very sensitive to a strange noise. You go, that doesn't sound like my car. That's because you're like the autocorrelator. You're like, oh, that sounds normal. No one told you that. You just learned it all by yourself. So we do this. Your brains are set up this way. We know this because we run psychological experiments on chess masters. So we'll show them a real game layout. And the better the chess player, the better they are at just seeing the game briefly and reproducing it. They see it for 5 seconds, and they'll put every piece on the board perfectly. That's because they've compressed down a way to think about the chess game. Novices don't do a good job. But here's the interesting thing. If you show an expert chess master a random game with pieces in places that would never normally happen in a game of chess, they are no better than the novice. That's because their anomaly detection hasn't worked. The chessboard went into their eyes but couldn't come back out their fingers. It's the same thing. So think how useful that would be in other scenarios, like once you've trained a neural net over and over with different numbers. Let me just keep going through this. Once that's trained, the dimensional reduction forces the model to learn feature chunks. And we're using this in a project at NASA Ames Research Center to analyze the electrical power right in the buildings that we use. So we track that data. It gives us all sorts of information about how the electrical power is used within buildings. So think of it this way. We can now use an autocorrelator to kind of just notice when something funny happens. Just like a number 3 would go in, not very well written, and the 3 that comes out isn't exactly the same. You might go, oh, that's not a good 3. Well, the same thing can happen with power. In goes the power, out comes the autocorrelator's reproduction of that, and you'd say, well, wait, that doesn't look like what came in. Over there, it's different. That's an anomaly. So in space, maybe there's a system watching all of the power systems within the spacecraft. And it doesn't have the answers. It just wants to say to the astronaut, that doesn't look like something I've seen before. That's like you listening to your car. Right? Okay, so that was a general introduction to AI. I'm going to move a little faster now, because now you're all AI experts. So think of it this way. Why do we need AI? Well, you know what? Antarctica is a difficult place to go. It's dangerous. It's cold. And when we explored it, initially, people died. It's hard to go there. Nowadays, it's very different, of course. You don't go to Antarctica to be brave and explore. You go to Antarctica to do amazing science and other things. Well, the moon is also a difficult place. And I'm here to say that Apollo lunar lander is the lunar equivalent of that little tent, right at the edge of what is technically possible, right at the edge of what is survivable. And space is dangerous. But we need to get to there, just like Antarctica. You're the ones who are going to get us there. And you're going to need AI to help. So human exploration, duration, environment, and the distance from help really defines how hard it is. All through history, we have explorers who have weathered danger, whether it's real or imagined, and accomplished wonderful things. And this is really where, for half a century, since the Apollo missions to the moon, This is what the astronauts' view in space has been. We're in low Earth orbit. It's not that far. The distance to the space station is about like going to Puerto Vallarta. Same distance. 400 kilometers, that kind of thing. Not that far. So in low Earth orbit, if there's a medical emergency, for example, you can be on the ground with a doctor in 3.5 hours. That's how fast they can do it. If you're going to Mars, the view out the window is very different. Earth is a tiny little dot. Imagine what that does to your brain, to your psychology, to your sense of loneliness. What does that do? No evacuation, no rescue. You're on your own. And we need AI to help make them safe. You can't even communicate. It's 25 minutes for light, for radio signals to go there and back. So no conversation. So it's a very difficult problem. Duration, these are permanent habitats or planetary class missions. Environment, you're in low or zero gravity, that does things to your body. Radiation and so on. It's a challenging environment. So just think of one example. For astronaut health, ultrasound is the preferred mechanism for doing imaging in space. And in the space station, the crew member there who might be examining another crew member who's not feeling well, he doesn't have to be a perfect ultrasound sonographer. He just has to put it in the right place generally, because the European Space Agency has a probe which can be manipulated using by a doctor on the ground. Right? It twists around and gets it just right. Well, Mars is different. You're 25 minutes away. You can't control it from the ground. That's not going to work. That's why we have solutions that are emerging, like companies like Caption Health, which have AI built into the ultrasound, so that it's looking at its own signal and telling the user, here's what you need to do. Rotate clockwise slowly. Move it this way, 5 centimeters. Because it knows you're trying to capture a good image, let's say, of a heart valve or something like that. Amazing stuff. So to jump into projects that I'm working on, and they all focus on space exploration, the first I want to talk to you about is a technique called deep reinforcement learning. And think of it like, in English, we call it trial and error. You try, it's wrong, you try again, you just do that over and over and over. But in the case of a computer, it does it millions of times. That's one of the key technologies that DeepMind used to create the world's best Go player, AlphaGo. So Go is, by most accounts, the most complex game ever devised by humankind. It makes chess look like a simple game in comparison. And the computer beat the best player in the world from Korea. And you know what's interesting? In an interview that he gave afterwards, he explained that he found it very unsettling. He didn't like being beaten, but that's not what bothered him. Go is so complex that as you're playing it, you can kind of sense the personality of the person you're playing. It's a psychology game as well. And it unsettled him to sense a deep personality in the AI system that he was playing. So, trial and error. It's an interesting technique. It allows you to move from the concept of just tactical steps, what should I do next, what should I do next, to strategy. When I lose, I go, oh, I made a mistake right at the beginning. I'm going to change my strategy next time. This is very powerful. So, for example, NASA looks at deep reinforcement learning to show how robots can adapt if something goes wrong, just like animals would. So a fun example here, they had a robot model. So this is in a computer saying, look, I'm gonna tell you that this leg here no longer works. You can't walk like you used to. Learn through trial and error, just by trying, how to walk without that foot. And it's kind of interesting. It sort of gradually learned to sort of lope along and barely touch the ground with that the foot. But then they did a mean thing. The mean scientist said, as a joke, well, now you're not allowed to touch the ground with any of your feet. Try that. And they thought that was funny, and they went home and came back the next morning, and the robot was very proud. It said, I've figured it out. I know how to do it. And then they asked to see how, and so the robot showed them. Now, it's funny, right? Because it's like a kid. It's like, I don't know what is going to work or what the rules are. I'm just going to keep doing what I did before. So, I'll just learn as I go. That's what I mean by AI sometimes having unintended consequences. In that case, it's fun, but we wouldn't want a system like this to flip upside down and crush all the instrumentation. That said, you can see the value. Imagine that one of those didn't work and it had to learn to continue the mission no matter what. So one project I'm involved in is trying to use deep reinforcement learning to get rid of orbital debris, which is dangerous, right? There's examples already of stuff we put into orbit impacting spacecraft. So we need to get rid of some of that. And this is well understood. If you look at some of the quotes here, this is essentially saying this is a big problem. We have to fix it. It's not just up to governments to fix it. I think we're going to need to have commercial companies help us. That's how big a problem we have here. So I agree. And I proposed this challenge to the public a few years ago to try and imagine an autonomous spacecraft which is powered by an ion thruster. So it's very light power, but it can go for a long time. So it only puts out about as much power as a coin in your hand. That's how much weight. But it goes and goes and goes, and can maybe visit not just one, but lots of different targets that all need slightly different orbits to intercept and remove. So it would fly by the object, eject a net, and then use electrodynamic dampening to deorbit it. So this was an interesting challenge. We used, as examples, real debris targets from a collision that occurred in 2009 between Iridium-33 and Cosmos 2251. So thousands of bits of shrapnel came from these collisions, and we want to get rid of them. So I put out a challenge to the public. I picked just 12 of the objects in the Iridium debris field. And a team based in University of Toronto used the Niagara supercomputer there to solve that problem. And they developed a new technique, a new function, the low-thrust RQ law, and succeeded in deorbiting all of those objects with very little fuel. Now the question is, how do we now scale up from 12 to thousands of objects? For those of you who are mathematicians, you'll recognize the orbital debris problem as being it's an NP-hard problem. That's the class of problem. It's like the traveling salesperson, but on steroids, because all of the cities aren't sitting still, they're in orbit, they're moving. So our hypothesis is that deep reinforcement learning will allow us to approximate an optimal solution, good enough, without it being the combinatorial optimization is exponential in difficulty as you scale up. But with AI, we could keep it linear. So that's a good example. A second example is, that I'm working on is in the area of astronaut health. And this deals with data that we collect on Earth before astronauts go on a mission and also once they're in space. So one thing we're very keen to do is figure out how can we monitor the health of astronauts without sticking things on them and taking blood. And, you know, being an astronaut is difficult. They don't want to be poked and uncomfortable. How can we monitor their pulmonary health, the health of their lungs? Because we know there's certain things in space. If they go to the moon, we know the lunar dust, it's called regolith, is very toxic. In fact, Gene Cernan was the Apollo 17 astronaut. That picture there, it's dark not because there wasn't enough light. He's covered in moon dust, covered in it. It sticks to you. And it's not like sand on the beach. There's no water or wind to round the shape. This is like little bits of glass in your lungs. It's horrible. So important that we know how to do this. Now, we were inspired by beagles, by a dog, because we know they can sniff breath. They can sniff blood samples. They can sniff urine samples. And they can be trained to say, this, I'm going to bark when I smell someone who has cancer. So we know the data is in the molecules that are coming off of the sample. We know the data is there. The dogs can be trained. So how can we make an electronic nose? That's what this is. So the e-nose is developed where I work at NASA Ames Research in California. And Dr. Jing Li is the inventor. I'm the principal investigator on how to amplify its capabilities with AI. So they're very good at threshold detection, how many parts per million of this molecule. But what about patterns of molecules that indicate different diseases, biomarkers? So we want to develop an AI model that handles hundreds of different molecules in a pattern that we can use for diagnosis. And we're excited because this captures an important part of what we do at NASA. NASA is, their mandate from the government is to explore. But another mandate they have is to take what they develop and show how we can help humanity with it as well. And that's what this does. Imagine a device like this where you could go to a remote community and help to diagnose malaria more quickly, or maybe embedded into a little air filter you might have in your bedroom. So when you wake up in the morning, it's Bluetooth connected to your phone, and it's like, you might want to set up an appointment with your doctor. Your breath was just a little off, and it's not that it smelt. No problem. It just, the molecules in it were not what I would expect. You should go get it checked out. And in fact, when you go to the doctor, imagine it becomes one of the ways you're brought in. Just like, okay, sit down, we're going to weigh you, take your blood pressure, your temperature, and breathe into this tube. Great. 10 minutes later, the doctor will see you, and by that time, they already have scanned you for 25 different diseases. So we're excited with where this might go. Another area of astronaut health that I'm involved in gets into these limited data sets. Now, I say limited, it seems so strange, right? Medicine is usually tons of data. But you got to remember, there's billions of us. But there's only a few dozen astronauts. We don't have a lot of examples to draw from. How do we know what happened? And here's the thing. Biology on Earth is not the same as biology in space. You change when you're in space. So all that data doesn't always apply in space. We have to start again. So we're often dealing with limited data. And we know that you change in space because NASA took identical twins, sent one to space, and one stayed on Earth. and they made them do almost the same things. Exercise, food, everything's the same. The only difference was one was weightless and in a space environment, and one wasn't. And a lot of things changed. Some of them not good. Your heart changes shape, your blood distribution, vascular system changes. So I was involved in a project with the Canadian Space Agency, who they developed this thing called the astroskin. So this is Canadian astronaut on the ISS, David Saint-Jacques. And it's wonderful because you don't stick anything on you, you just wear this vest, and the biosensors are kind of woven into the fabric, so it's very comfortable. And we wanted to use it to monitor the heart health of astronauts, ECGs. So normally when you have an ECG, a doctor looks at it, but we wanted a computer to watch it all the time, 24 hours a day. And so think of it this way. We wanted, remember the example I showed you where it could take a 2 and figure out, oh, that's the number 2? Do the exact same thing, but this time the input is an ECG, and it goes, oh, you've got atrial fibrillation. That's not good. It's just a different set of data. And so the problem we had was, where do we get data that shows an astronaut having a heart problem? We don't have that. Very few incidents. In fact, there's only really one. This is the only ECG I'm aware of showing an astronaut in orbit having a heart problem. And that was way back in 1970, I think. And it was just very brief. So that's our problem. How do we train the neural net when we have no examples to use? So what we did was we used generative AI. So generative adversarial networks, you've heard about generative AI. That's what's behind ChatGPT and things like that. It makes new stuff. That's its job, make new data. So you can, for example, and this is real, this is a real system, you may have seen it, show it lots of examples of famous paintings by certain artists. Then you can show it photographs and say, make a painting of that image, that photograph, as if it were the artist. And it does a pretty good job. It goes, okay, I understand sort of the style of the artist. So these work. And so what we said was, well, look, why don't we sort of do something like that? The style is the heartbeat of an astronaut in orbit wearing an astroskin. The photograph is someone on Earth having a heart problem. And the blend of those two is what an astronaut in space would look like if they're having a heart problem. So we did that. We created a neural network, and this is back in 2018, that did a generative AI model, quite complex architecture. And the output we were very encouraged with. Doctors looked at it and went, yeah, that looks about right. And in today's environment, that's kind of a gold standard. But also mathematically, we showed that the black dots are humans on Earth having a symptomatic ECG. They've got a problem. The red dots are astronauts wearing the astroskin with no heart problems. And the blue dots are what this system output, which is mathematically kind of in between the two. So we feel confident that we could generate lots of blue data and train the model using that and detect a heart problem of an astronaut in orbit successfully. So we got around the too little data problem by making more data ourselves with AI. Another opposite problem is when you have too much data. So the challenge of spaceborne data, biology data, let's say, from astronauts in space, is it's sometimes huge. There's not many astronauts, but we collect a lot of data from them. Here's the problem. All through history, this goes way back to like the telegraph, we have created data much, much faster than our ability to transmit it. So for the mathematicians in the room, this is a logarithmic scale. So just imagine the exponential curves. They're insane. we're generating data sets that are so huge compared to our ability to move the data around. That's why we often, to put it, one way it's phrased is you move the question to the data, not the data to the question. You move the computing power to the data. Leave the data where it is. Now, that problem of moving the data is why companies like Amazon offer this. They did the math, and they found out that you can move more data from one place to another faster, so that's more bytes per meter per second, by putting it in a truck, petabytes of data in a truck and driving it at 100 kilometers an hour than you can over a fiber optic line. Like, that's the math, because we're so much better at storing data than we are at transmitting it. Now, spaceborne data is going to be no different. We'll have the same issue. That means to me that pretty soon we will not be able to downlink to transmit back to Earth all the data we make. Now, is that a problem? Or is this something amazing? I think it's something amazing. I think it's something that is going to affect all of us soon, and you especially. I think of it as being a milestone when human knowledge will finally and forever span more than one celestial body. We won't bring it all back to Earth anymore. We've expanded as a species and become a spacefaring species. Our knowledge now goes to the moon and Mars. It's wonderful. It's amazing stuff. Now, a project that I'm the principal investigator on, and actually, coincidentally, today we're running an important test with the Earth replica of the systems we're about to use in space, is a project called Fluid. And it's run with several partners we have along the top. Federated learning is a technique where you leave the data where it is. You don't move it around for the reasons I mentioned. It's going to be huge. But you can still train neural nets as if you had brought all the data back down to Earth. You don't do that, but it looks like you did. So that's federated learning uses a technique to move little bits of the model up to where the data is, and train data models in the NASA Human Research Project labs or in our gene lab. And then you consolidate it again to a brand new model. That one looks it's as good as if you had brought all the data together. You move little bits of the data around, little bits of the model, not the data. So it adds complexity, but it works. So we're excited about this. This is a way of leaving data in space and combining it with data on the ground and moving AI forward. So why would we do this? What sort of benefit would it have? Why does this matter? I think it matters. Sorry, I'm just trying to. That's the computer we're going to be running it on in space. That'll happen in about 2 weeks. And in space, transmission of data is even harder than here on Earth. So this is important. Now, it matters because of this. Here's one project we think will follow. If Fluid is successful, we want to start applying it to real problems that matter to NASA. If you look carefully, something interesting here, almost half of NASA's astronaut corps are female, which is fantastic. In fact, did you know the next mission to land on the moon, Artemis 3, is going to have the first woman to step foot on the moon, which is magnificent. Now, historically, the astronaut corps has been mostly fighter pilots, test pilots. They've been men. And we've put a lot more time, because we've had an effort into understanding male biology in space, male health in space. It's just the history of it. But now, that's not good enough. So one project we'd love to do is to analyze and project the risks to female reproductive health in space. Is there a risk to female astronauts that they may have more miscarriages, they may have more fertility problems because of the radiation they've experienced or weightlessness. How can we figure this out? So the plan is to create a lot of data on Earth using, we're actually going to use rats as an animal model species. A lot of, for if there are biologists in the room, this is RNA data, transcriptomic data. That's a lot of it. And do the same thing. We're going to take frozen eggs from a rat and analyze their RNA and the transcriptomics in space. That's huge, that database. We do not want to downlink it. But what we will do is use that fluid technique to train a little bit of the model in space, a little bit of the model on Earth, and combine the two to become a predictive model to help us understand what can we use to predict how female health in space is going to evolve over time? Are certain women with certain DNA markers more at risk than others, et cetera? Really important. Because the thing is, space doesn't look dangerous here. This is finally a moment of relaxation for this astronaut. Jessica Meir, she's quite famous because each astronaut gets a very limited budget for how much they can carry into space. They weigh it. It's like, you're allowed, this many grams. She used almost all of her budget on a saxophone. That's how important it was. Good for her. But believe it, these are brave people. These are like the individuals I showed you earlier in Antarctica. It's hard. So the least we can do, the least you can do, is to give them every bit of assistance you can to make them safe, to make them successful, to keep them healthy during the mission, to keep them healthy when they come home. They need your help. And I think you will be more successful in helping them if you use AI as a tool than if you try to go it alone. And that's my belief. And I think that's good for humanity. I think it's good for all of us. And on that note, I want to thank you for allowing me to tell you why I'm excited about AI, acknowledge why we need to be careful, but most importantly, to thank IBERO and AEM for allowing me to come here to speak to you. That's why I said I'm here to see you, not the other way around. Remember, you're the ones that are going to do this. So I really hope some of these ideas have encouraged you to get involved in AI for the good of humanity. There's so much we can do. Thank you kindly.
Muchas gracias a Graham por compartir su conocimiento. Querida comunidad, hemos llegado al final del evento. En nombre de la Universidad Iberoamericana Ciudad de México y de la Dirección de Educación Continua, agradecemos nuevamente la colaboración de la Agencia Espacial Mexicana, al igual que el apoyo de nuestros patrocinadores, GEMED, CDO y Valencia del Toro. Gracias a todas y todos por su presencia en esta conferencia magistral. Pasen muy buena tarde y hasta pronto.